Turn off the top lights.
Yes.
Okay. Start off with why is the sky blue? Anybody? No? Close, Michael. Blue light gets scattered by the atmosphere. So light enters the atmosphere, it hits like a molecule of air, usually nitrogen, and it hits nitrogen, and the blue light gets scattered in all directions. And that blue light that gets scattered in all directions again. So it keeps getting scattered, so it looks like the blue light's coming from everywhere in the sky. Does that kind of make sense to everybody? So if we didn't have an atmosphere, like on the moon for example, it would just be the sun and everything would be background, just like at night. Which would be kind of creepy in my opinion. You'd also be able to see stars at night, during the day as well, as long as you're looking near the sun. I think it would be interesting to see. You can go to the moon and experience it if you want. Hey, everybody understand why the sky is blue? No? So light comes from the sun, hits molecules in the atmosphere scatters blue light more than any other light. So blue light gets scattered, and then the light that got scattered hits another molecule, gets scattered again, gets scattered again, gets scattered again. So it looks like the blue light's coming from everywhere. That's why the whole sky is blue. And the atmosphere actually scatters all colors of light, but it scatters blue light the most. Does that make sense?
So why, when you look directly from the sun, if it's such white light, why doesn't it scatter the blue light then?
Well, the light directly from the sun is still being scattered, but that's all the light's coming directly from the sun. So like, the blue light you see from the sky is coming from like over here, after it's gotten scattered. Alright, mirrors. Everybody looked in a mirror before?
Nope. They all break. They all break. I'm sorry. Every day.
Okay.
I threw a rock in.
We're a beautiful class if you want to.
They are a beautiful class. Alright.
You should.
So, anybody know what this line right here is called? We talked about
Symmetry.
symmetry. Close. It's a line perpendicular to a surface. Starts with an N. Ends with an ormal. Normal line.
Normal.
Normal.
Okay. So if you draw a now you got me saying it, Michael. So if you draw a normal line, the angle between the normal line and the ray of light coming in is equal to the angle between the normal line and the ray of light coming out. So the important thing about mirrors is the angle of incidence equals the angle of reflection. So it comes in at a 45-degree angle, it goes out at a 45-degree angle. Make sense? Okay. So how a mirror works and why you see the images behind the mirror. So let's say there's a bee here. You look at the mirror. The light comes from the bee, bounces off the mirror, those two angles are equal, goes to your eye. You interpret that as seeing the bee where that light ray would come from. Does that make sense? So this, like this distance and this distance are equal. So look, the bee looks the same distance away as like from there to there, but it appears like the light's coming from inside the mirror, so your brain interprets that as being inside the mirror. Does that kind of make sense to everybody? That's an important concept as you go over some other things later on, is that wherever the light ray appears like it's coming from, that's where you see the object. Does that make sense? And if you're looking at a mirror, you know it's not there, but that's where it appears to be. Any questions about that? Alright, refraction. How many of you guys have ever noticed that if you're like looking at something in the water, you try to pick it up and it's not where it's supposed to be? Alright, let's do something called refraction. So when light goes from one thing to another, it bends. And if it goes from something less dense into something more dense, it bends toward the normal. If it does the opposite, it bends away from the normal. So what happens, I lost my train of thought. What happens when you're looking at something in the water? Say, there's a fish here. Here's Michael with a spear gonna stab the fish.
Wait, which Michael?
You.
Of course.
So the fish like comes from the fish out of the water and gets bent away from the normal line like that toward your eyes. So if you trace that back, the fish actually looks like it's right there. Does that kind of make sense? So everything looks a little shorter in the water. You guys noticed that before? And that's because of the refraction of the light coming out of the water. Does that make sense? Another analogy for this refraction thing is, has anybody driven off the edge of the road before?
I did
Not
driving school. I had.
No, not on purpose. On
I actually
purpose?
did on
That makes it
purpose,
worse.
yeah.
What?
So, when you drive off the side of the road, does anybody know what, like your car pulls one direction, which way does it pull? Off the road or on the road?
It's just
Off the road.
Off the road.
So what happens is, when you hit like the dirt or the gravel or whatever, that side of your car slows down, and since it slows down, the other side is speeding up, your car tends to pull that direction. The same thing happens to light. So if it goes from here to here, it slows down as it enters and it gets pulled this direction. If the opposite happens, so if it was going like out of here, it would get pulled away from the normal. Does that kind of make sense to everybody? Alright, you guys can understand the refraction thing? That light bends, that's why how glasses work, and we'll talk about that more later on when we get to lenses. Alright, sunsets are red, not blue. Can anybody make a guess why sunsets are red?
Because it's so much lower than
Brian.
it was.
Because when the light takes longer, like I don't know, like the light that hits the atmosphere is like the red part of the spectrum. So when it hits the atmosphere, it breaks apart.
You had a good idea at one point, but that's not quite it.
red light gets scattered. Blue light slows down more.
What?
Light slows down more.
What happens at sunset? This like, does it light go through more of the atmosphere at sunset or less of the atmosphere? More. So what happens? So if you look at, let me draw a diagram here. Might be better to draw. So there's the Earth. The marker that works. There's the Earth. There's the atmosphere. So at noon, when you're standing right here, sunlight comes in. There's not much of the atmosphere to go through. At like, as the sun is setting, the light goes through a bigger portion of the atmosphere. So what happens at sunset is the blue light continues to get scattered, and gets so scattered it kind of becomes less present. But red light and yellow lights and orange lights get scattered a little less than blue. So they make it, and now they're scattered enough to make the whole sky look red. Does it kind of make sense? Right?
So the sky is the bluest at noon.
Sky is the bluest at noon, yeah. I mean, it's going to be the least red at noon. Probably erase these drawings. Alright, how many of you guys on like a hot summer day have ever seen water on the road that's not actually there?
What if you see it on a cold winter
I
day?
don't know about that.
You can see it on a cold winter day as well. Do you guys know what I'm talking about though? Like it looks like wavy, it looks like there's a big puddle of water there. And no matter how, it's actually exactly what a mirage is.
I got it. Oh, wow.
And you never get to that water, it just keeps being about the same distance away. You know that too, I assume? It was actually, if you actually drive through the water, that's not a mirage, it's actually water. Okay, so what happens is you have warm air closer to the ground and cooler air above it, and because it's two different densities, the light gets refracted. So let's say there's this tree over here, light goes down, it gets bent up towards your eye. So normally, if that was happening, there'd be something reflective like right here. Like, say there's a puddle of water right there. So normally, if it's bouncing up like that towards your eye, there'd be something reflective there, reflecting the light. But instead it's getting bent. But your kind of eye and brain can't tell the difference because the light's taking the same path when it gets to your eye. It looks like it's being reflected off the surface down there. So the light behaves exactly like it would if there's a puddle of water there. So that's why you see it looks just like what there's a puddle of water there. And it's also not consistent heating, so that's why you get kind of the wavy pattern, so it looks like a wavy puddle of water. But it behaves just like it would if there's a puddle of water there. And it's most common to have something like this in the desert, because that's when you really notice it. If you're walking across the desert and you're really thirsty, and it looks like there's a puddle of water ahead, you keep walking toward the puddle of water and it keeps getting the same distance away, it would have to be like insanely frustrating, I would assume.
So do we see the water because we expect there to be water there reflecting, or is that
It,
just...
the light does the exact same thing as if there was water there. So there's sort of a, and I showed you that TED video about like perception. There's lots of different ways for light to get to your eyes in the same way. So in this case, light will do the same thing if there was a puddle of water there, or if the light was bending. It's much easier for your brain to process being a puddle of water there. Like that's what's most common in your experience when you look down and you see a reflection off the road, it's a puddle of water. So that's what your brain is kind of wired to assume. Does that make sense? And it looks like the same like it would be. Questions about that one? And so you'd also see whatever is over there, but alright. Total internal reflection. Erase my garage drawing here. Okay, so you shine like a beam of light out of the water, goes out. If you shine at a slight angle, some of the light goes out, some of the light gets reflected back down. As you keep shining at a greater angle, it keeps getting bent more and more. At one point, it's going to get bent so much that it's not going to come back out. Does that make sense? That's called total internal reflection. Have you guys, you know those little they're like this white little plastic fibers that come out of like a little flashlight? You guys know what I'm talking about? You can get them at like King's Island or something like that.
Yeah.
Yeah, the little fiber optic things. Those operate on total internal reflection. So if you look at one of those, you turn the light on, none of the light comes out of the sides of the little wires, little furry things. It all comes out the end. That's because those wires are like the little fiber optic cables that are designed to totally internal reflect no matter what angle they're at. So the light stays in that little like tube, I guess you can think of it as, until it gets to the end and then it comes out and you can see it. That's why the ends all look bright, but the middle doesn't. Everybody kind of understand that? And that's, you guys heard of fiber optic cables, I assume? So fiber optic cables, my guess is most in your house have been, the ones to your house have been replaced, like copper wire has been replaced with fiber optic. How those work is they shine, instead of electricity pulses to transmit information, they use light pulses to transmit information. And it's much more efficient to use light pulses than stay in the wire and get to the other end. So they basically, simplified versions of turning a flashlight off and on at one end, and then there's a sensor at the other end to see if the flashlight's off or on, and that transmits the information. And they're much more efficient. So like a fiber optic cable that's like the size of a pen can transmit the same information as like a copper wire cable that's like the size of your arm. So like no matter how you bend them, the light stays in. Eric?
This isn't one of those, like a big fiber optic cable going like across the Pacific Ocean or something.
There is a cable that goes across the Pacific Ocean. I believe it is copper wire. They may have laid down fiber optic, but that was like a big deal like in the early 20th century that they laid down, like they took a boat and literally like dropped a giant telephone wire essentially across the ocean so that they could communicate across from Europe to North America. I believe that is still there as far as I know. And it wouldn't surprise me if they're done it with fiber optics as well, but I'm not sure. Alright, rainbows.
Yay.
Yay. Anybody know the setup necessary for you to see a rainbow? Where does the sun have to be?
The sky.
The sky.
Is the sky?
Behind you.
Has to be behind you. Where does the rain have to be? In front of you. So what happens, the sunlight enters a raindrop, it gets refracted, so it gets bent, but each different color of light gets refracted a little tiny bit differently. And that's true no matter what it's going into. So it gets separated a little bit, then it gets totally internally reflected off the back. So the angle is like low enough that it bounces off the back of the raindrop. And then it gets refracted again at the coming out, and it gets separated a little more. So if you're standing here, you see all those colors get separated. And because the raindrop is spherical, you get a spherical shape. So actually a rainbow continues all the way around in a giant circle. We can't see the other half of the circle because the ground gets in the way. So what you're seeing is the light bouncing off the raindrops and coming out and being separated by refraction.
So
Yeah.
when you see a rainbow, like if I see a rainbow here, could it be seen anywhere around the world? Because you said it kind of goes in a circle.
It goes in a circle like if you're looking at it it goes in a circle like that.
Not around the
Not around the world.
If you had like a big piece of paper or something, and you looked at the right angle, could you see the other half of the circle?
Like if you had I believe you could. I mean, it'd be obviously difficult to do, but yes, if you had something that would like make the rainbow appear, it would I think it would appear on the ground. I'm not 100% sure on that. I feel like it should, because part of the problem would be that you'd start there's only a certain place where you can see the rainbow. Like this is coming to you. It's either gonna if you're too close to it, it's gonna go over your head. If you're too far away from it, it's gonna hit the ground first. So you're not gonna see that light. So I think you might at some points on that giant sheet of paper, you wouldn't be able to it would be outside of where the rainbow would appear. Does that make sense? But so there's a certain region where you can see a rainbow. So if you get too far away from it, it'll disappear, and if you get too close to it, it'll disappear. Too close to the rain, it'll disappear as well. So if you're standing here, you're not gonna be able to see it. You gotta be standing right here. That's why you can never catch a rainbow, because you'll just run into the rain. That's where the rainbow actually is, and then you won't be able to see it anymore.
Okay, do you have to have a certain size though? Because I know it's usually only when there's sprays of it that you can really see it, not when it's big, huge globs. You know what I mean? Of rain. Does it matter the size of the drop? What?
The drops
Well, that's a legit.
need to be the size of the drops will affect the kind of the shape of the rainbow to an extent,
Okay.
because the lighter the drops, the more spherical they are. So you're probably correct in assuming that lighter rain creates a better rainbow, because the heavier drops fall faster, so they're going to have more of the traditional raindrop shape.
Yeah.
I'm guessing those don't form a rainbow quite as well.
Okay, because don't natural rainbows are usually after it's already done raining.
Natural rainbows are always after
there's still
you have to have the sun behind you
Right.
and the rain in front of you.
Okay.
So it's possible that it can be the rain can be coming and you can see a rainbow, but it's in general partly because storms usually usually where you're going to get this is a storm coming through and storms usually happen in the afternoon, so you have a storm coming through and then clear sky after it. Usually if it's really light rain, in the morning or something like that, it's just kind of cloudy right after the rain.
Right.
Sean?
But why don't you see a whole wall then, if it's just the light reflecting off the light drops? Why is it just one thin thing?
So, again, it's because as you get closer or further away from the rainbow, that band will shift up and down. Does that kind of make sense?
That's just where the light.
Yeah, it's just where that light gets to your eyes is where you see it appearing. So I guess technically it would be a giant wall of rainbow, but at some point, if you get too close, it's not going to be this big if you're really close or something like that. But it shifts up and down as you move. So it's just what reflected light you're seeing. Any other questions about rainbows? How many of you guys have read Hitchhiker's Guide to the Galaxy?
Sorry.
This is
You can explain it still.
it's according to Hitchhiker's Guide to the Galaxy, 42 is the answer to life, the universe, and everything. And this is one of the places that people think the author of the book might have got it from. This is the angle of a rainbow. Alright, and mirrors here. Okay, so if you have a curved mirror, you can have, Michael, any of you girls have a mirror that is a magnifying mirror?
Yeah.
Any of you guys have it with you?
No. Sorry.
Need to go get something. I'll be back.
Okay.
Okay.
Should
Have
we
a
stop
safe trip.
Should we stop the video?
Let's talk to him.
Okay.
Alright.
I'm good, Aaron.
Hey.
Here we go, Knights.
But I'm not gonna say it.
Go Eagles.
Say it.
I've heard words. Say it.
Hey, it's me, Michael Spencer. Are there any CJ chicks out there that want to get a piece of this? I'm real good at b-ball.
Yeah, I stop. Okay. Do you,
Have a good day.
We know a little bit. Okay.
Open it?
Yep, like the blinds. Alright. So a concave mirror can magnify things. So like if you're looking at your face, you can see it magnified. Other thing, actually let's go to a convex mirror. So like concave mirror, the mirrored side is on like the cave side. Does that make sense? It's like if you make a cave with your hand, the mirrored side would be like inside the cave for concave mirror. So it focuses the light onto a certain point. Does that make sense? A convex mirror is the opposite. So it's, if you do your hand like this, it'd be in your palm of your hand. So that's convex, concave. And a convex mirror spreads everything out. So a good example of a convex mirror is like the one in the right side of your car, the rearview mirror. It spreads the light out and it makes everything appear smaller. So a convex mirror will increase your field of vision because it makes everything appear smaller. Does that make sense? So that's why it's used in like, the other place it's used for is like in the corners of like shopping, usually like drugstores. So they can like see you stealing something. Alright. And next thing I want to talk about is real and virtual images. A virtual image is an image that appears behind the mirror. That's what you normally think of, like in a flat mirror you see a virtual image. So a virtual image is one that you'd have to like, in order to touch the image, you'd have to like reach through the mirror to get to. Does that make sense to everybody?
Yes, sir.
A real image has to be projected onto paper. I'm going to use this magnifying glass here to project a real image from outside because it's just easier than using a mirror. So actually,
Got it.
I'm going to grab the camera there. I'll come around and show everybody this. Right.
Whoa.
It's
trippy.
So you see how the trees and stuff outside, they're upside down. Okay, you're going to have to do that.
Wait, who? Someone just moved in the way.
You can see like the sky.
I mean, you
So
can
that's-
totally see something. I mean,
It's probably much cooler in person.
Yeah,
it is much cooler in person, but they get the gist of it. It's fine.
So that's an image of what's outside. That's a real image. Yeah, I'll come and show you guys over here real quick. Actually, why don't you guys all just come over here? It's easier.
You just got on video.
Did I?
Yeah.
And is that a concave?
This is a.
Your butt did at least.
We'll talk about that.
I missed it, Laura. Don't
So
worry.
you can only make a real image with a concave mirror. So I can do this with the mirror as well. It's just more of a theme. You get a better image with a.
It looks better when you work.
Has everybody seen it? Yes. Come down.
I didn't. So Michael's butt though. I walked around.
All right.
best feature.
That's gross.
Is that the end of the note sheet you guys have?
Yeah.
So we'll stop. Alright, let me go find one more demo here that you guys like. Another example of a real image that's even more interesting.
Why do you have that around? More interesting.
Michael, hit this. Ready? Oh, I'm not gonna. Just punch it.
I heard you lost it.
Heard you would. Kira!
I'm gonna read over this.
I put a no sign on it. You're off.
Alright.
Subscribe to the Snapchat channel.
You need help?
What was it?
Okay. Who do I want to mess with?
Me.
Typical Brock.
You don't have to be on camera, you just have to watch the.
Okay, I can watch it.
Hey, I forgot.
This is giving me headaches.
There's Michael.
Let me go grab some.
Okay.
Hey, it's me, Michael again.
Let's look into the mirror.
I'm looking for a foxy dude for prom.
You can't see anything. It's freaking me out. I'm not seeing it. Oh yeah, we can.
Why do you use me?
See, I can move down.
Alright.
Because I made my voice deep like it.
You've been going.
25 minutes. You're going strong.
Okay. So try to grab the pig, Kira.
Oh God.
The what?
The pig.
I'm scared.
The what?
It's inside, isn't it? But it looks like it's on top. There's nothing there.
Can you see it in the camera, Chloe?
Sort of.
Ready? Can you see the
Oh
pig?
yeah, I
Ready?
can see it now.
Like, there's no pig there.
What?
Grab the pig.
Oh, there it is.
That's true.
Hey, piggy.
Grab the There's nothing there.
Don't stick your fingers in, okay?
Piggy.
Ryan, you'll scratch the mirror and it won't be as clear anymore.
Why isn't piggy
Wow.
There's no
That's
pig there.
Because it's.
That's definitely cheating.
Oh my gosh, that is.
Can you tell us to
You can mess with little kids.
Yeah.
If you don't stop touching it, then it looks real.
That is so.
There you go.
Anybody else want to try it?
Yeah. Can't pick it up.
Touch the piggy.
Sorry.
That is
See,
so
look,
crazy.
it's just, oh, no.
Alright, so that's another example of a real image. This is two mirrors generating the real image.
I don't like this.
So what's happening here is the pig is it's right directly below. So light reflects off the pig, hits the top mirror, so this side is mirrored as well.
Oh, it's flipped
there's
the
a
other
real
side
pig
too.
in there.
It looked like it was facing the other way.
Yep.
Oh my
So it's reflected
Well, now it's
off
on
the
the
top mirror, then to the bottom mirror, then up to your eyes. So it looks like the pig is like sitting right here, but because of how it's shaped,
gosh.
it ends up appearing like it's right there on top.
Oh my gosh. Like it's not there. This is not real.
Michael just crosses the line.
No, not there.
Got it.
Oh, that's what I was looking for earlier.
Why can't I expose this to direct sunlight?
So guys, these mirrors have to be like perfectly shaped, otherwise it'll be like, the pig will be like all wobbly and like not look real. Or if you scratch the mirror, it looks like kind of blurred.
Yeah.
So you gotta kind of be careful with the mirrors, otherwise it'll like not work as well anymore.
Why can't you put it in direct sunlight?
It'll warp the mirror a little bit.
Oh.
You can turn off the camera now.
Have a good day.